All right. Hello, everybody. Okay. Let's get going. I'll do the clap thing. Clap if you hear something. All right, we're done. It's not my vibe. I don't know. Anyway, all right. So it goes. What? Twice. Okay. It didn't work. I didn't say clap. Okay, you got to own the room and make it happen, but it's just not my style. I need like a different thing we need to do, like jumping jacks, but I don't know. All right, so we're going to pick up where we left off last time. I had a bit of a slide desynchronization issue, so I'm 99% sure in the second part of this we're going to end up having a couple slides that are slightly wonky. Sorry, it was stressful. But I'm going to pick up where we left off last time, wrapping up our discussion of Notes 14 by talking about independent events that are not independent and trying to talk about the product rule. I got to do the clap thing. Okay, clap if you can hear me. Twice if you can hear me. 317 times if you can. I just can't stop. I'm disrupting my own class. All right. So what we were working on is we had talked about this idea. We had this nice rule here we derived, which was that the product of the intersection of two events was the product A1, the probability of the intersection of two events was the probability of one event times the probability of another event given that first event. That's something we spent a lot of time deriving that formula last time. And so what I started doing last time is saying, well, how do I generalize this to more than two events? So if we have three events, I didn't show this slide last time, but I decided to retcon the lecture and talk through this. If we have three different events that we want to find the probability of their intersection, then we could say that the probability of their intersection is just the natural extension that we take A1, its probability, times the probability of A2 given A1, times the probability of A3 given A1 intersect A2. So how do we show that? Well, all we got to do is realize that this right here, if I take this and I apply this definition, if I multiply these two probabilities, that's just the probability of their intersection. So these two things are just this. And then if I multiply these two events, well, A1 intersect A2 is just an event. Like I could temporarily call it like Q. So it's probability of Q times the probability of A3 given Q, and then we get this final intersection of all of the rest. Okay? And we can keep going, and we could generalize to any number of events. We could say, if we want to know the probability of many different intersections, let me give you an example. It'd be like the probability of getting an ace of spades, or sorry, a three. The probability of getting like an even number and a number less than 3 and a number which is prime. Those are all different events you might have if we're rolling dice or something, right? So no matter what events you define, doesn't matter if they have some relationship, the product rule always works because this top expression always works. There's no assumptions about the events, okay? And so forth. So this right here, notice the key idea is that we're going to have this is going to be useful if it's ever the case that we can ask ourselves, what is the probability that event 4 happens given that all of these happen? And if I'm able to do that kind of decomposition, I can get a simple expression. Okay, so we're going to spend a lot of time playing with this rule we've derived. And so I'm going to start by, well, actually, I'm going to show you the most general version, which is what does the last term look like? So if I just keep going, if I have n events, and I want to know what the last terms are, the very last one is the product or the probability of the last event given that all of the other events have happened. Okay? And we're going to prove this in a bit, but first I actually want to get some familiarity with what it even is before I prove that it is true. So this is the product rule which we are partially done with in the previous lecture. And so I'm going to show you why this might be useful. Let's imagine we want to know the probability that we have a flush of hearts. Okay? So these are example heart flushes. And we already saw how to do that before. What did we do? We counted all the ways to get a heart flush, and we divided by what? All the possible combinations of cards. Okay, this is a different approach that's less tedious. And what we're going to do here is A is going to be the event where we get a heart flush, and it's going to be the intersection of each of these different other events. AI is going to be the event where the ith draw is a heart. So maybe you got an ace of hearts, then a 2 hearts, then a 5 of hearts. So A1 means your first draw was a heart. A2 means your second draw was a heart, and so forth. And so what we can do if we write it in terms of this intersection, we'll be able to use the product rule and get our answer with less pain. And this might be, when you were doing homework 8, you might have been informally using this without really thinking about it. Okay? So we can write this using the product rule. If I just do it mechanically, the product or why I keep saying product. The probability of A1 times the probability of A2 given A1, and so forth. And what's nice about this is that each of these individual 5 probabilities is relatively easy to compute. So for example, what's the probability that our first draw, if we draw a card out of 52, is a hearts? What's the chance that I get a hearts? 13 out of 52, I heard someone say, which is just a quarter. Okay, that one's pretty good. Now, if we've already drawn a heart, what's the probability that the next card is a heart? Yeah? 12 out of 51, that's exactly right. And then we can keep going. Okay, so we know these first two are 13 52nds and 12 51sts. What about the third one? What's that one going to be? 11 out of 50, exactly. And we just keep on going, and we get this nice little expression that gives us the probability of a heart flush. It's a lot more convenient than what we did before, where we had to say, what's the size of A? If the A is the set of all heart flushes. And what's the size of all of the possible draws? That's the omega, our whole sample space. And this is a much simpler approach. You can also think of this as like the tree diagram. You go down the 13 52nds branch, then the 12 51st branch, and so forth, until you get this heart flush. Okay? Any questions about this? So the product, yeah.
How many decks are used in poker, just in general?
In a normal game of poker, how many decks are used? I don't know. I mean, it depends. If you're playing, who plays poker a lot? Someone in this room surely plays poker a lot. Do you use one deck? That's what I was assuming. But maybe there's a crazy version where you have more than one. Yeah. Blackjack's the one where you have multiple decks. I don't know. I knew that answer. If you played poker with multiple decks, that would be crazy. Really upsetting. It would mess the whole game up. All the things you spend all your time memorizing wouldn't work. All right. Another example, Monty Hall. Now again, this is sort of a funny thing to use the product rule for, but it's to show you the universal applicability of the product rule. We remember last time, or no, 2 times ago, we showed the probability of all the different combinations of contestant choosing door, prize being behind door, goat being behind door. And we showed they were all either a 9th or an 18th. You could use the product rule even in this sort of complicated situation. So imagine I wanted to know the probability that you picked 1, that the car is in door 2, and that the host shows the goat behind door 3. Well, one way I could write the product rule is as follows, though there are other combinations. But if I pick C1 first, then it's going to be C1 times the probability of P2. That's the event. Sorry, P is sort of a double used here. Bold P is probability. Non-bold P is this event, and so forth. So this is just the product rule. And so we can work our way through this. What's the probability that I choose door I randomly? 1/3. What's the probability that the prize is behind door I, given that I picked 1/3? What do you think? A little tricky. Also 1/3, because they picked the prize door without knowledge of what I did, so it's actually independent of my choice, but fine. So that's also 1/3. And then what's the probability that the host shows that there is a goat behind between door 3 if I picked door 1 and the prize is behind door 2? 1, exactly. So I multiply those out and I get 1/9. And that's one of those diagrams we had when we showed, one of those probabilities on the big sample space we had before. Okay. And the notes talk about this a little more, but I don't care that much about it. Yeah. Right, so if I picked door 1 and the prize is actually behind door 2, the host can only pick door 3. If they picked 1, the rule of Monty Hall is they never show what's behind my door, and they never show the actual car. Does that make sense? They'll never show the car. Right. So they definitely will show the goat behind door 3. Does that make sense? Okay. As an example of a totally degenerate case, you can also apply the product rule if all of the events are independent of each other. You would never do this, but this is just a showcase. This is truly a universal rule. So let's say we have 3 independent coin tosses, and A is the event that all of the tosses are heads, and A1, A2, and A3 are the event that the ith toss is heads. So we could write out the product rule as follows. The probability that they're all heads is the probability that the first is heads, times the probability that the second is heads, given that the first is heads, times the probability that the third is heads, given that the first two are heads. Okay, this is definitely a true statement. It's not particularly enlightening because, of course, the probability that the first flip is heads is what? If it's a fair coin? Half. Okay, that's going to be half. And what's the probability the second flip is heads if the first one was heads? Also a half, which is why I just wrote probability of A2. So here this is a degenerate case because they're independent events, so the overall probability is just an eighth. So it works even when there's dependence between, or even when there's no dependence between the events. Okay? So it worked with flushes when they had dependence. It worked with Monty Hall where there's a mixture of dependence and independence, and here it also works when they're all independent. Okay? All right, so that's what the product rule is all about. We're going to use it again later for solving the birthday problem again more easily. What I will say in general is that in homework 8, you probably spent a lot of time thinking about the sizes of sets. The product rule is a way that you can often avoid thinking about the sizes of sets. It saves you some work. Okay? So why is it true? Okay, a lot of algebra coming at you. So this right here is the product rule in its most expanded form. Okay, I think it's nice to see all the terms for this proof. So the probability that all of these events happen, I just said, is the probability that the first one happens times the probability that the second one happens, given the first, and so forth, all the way to the very end. And I want to prove to you that this is true by induction. Okay, so I'll start with the base case, which is that n is 1. Obviously, the probability that A1 is probability A1 happens is that the probability that A1 happens. Okay, and you can bold these p's if you want to be consistent with the notation elsewhere. Okay, now the proof by induction step, or the inductive hypothesis and induction step. So what I'm going to do is, in order to make the algebra cleaner and not have to do any typesetting, I'm going to do a little weird where I'm going to say the inductive hypothesis holds for n minus 1 and prove that it holds for n. That's the same thing as saying it holds for n and then showing it holds for n plus 1. But I'm just starting with a different number. This should be fine. And so I'm going to assume my inductive assumption, my inductive hypothesis, is that it works for n minus 1. Okay? And I've color-coded everything to keep track of all the little bits because there's just so much stuff on the screen. So my inductive hypothesis is that the probability that the first n minus 1 events is obeying the product rule, as you'd expect. And what we want to show is the top line, which I've rewritten here. So this line right here and this are exactly the same. So I want to show if I go up to n, that it is still true, and then it's just this original term, but now multiplied by one more, which is this green one. Okay? So how do I do this? Well, I'm just going to do a little bit of algebraic manipulation. It's a proof there's a lot of symbols, but there's not much cleverness behind it. Okay. So first I'm going to observe that I can rewrite the probability of the intersection of all of the events as the probability of the intersection of the last event with the intersection of all the other events. Right? And that's just like, ordering your parentheses with an addition statement. 3 plus 4 plus 5 plus 6 is the same thing as 3 plus 4 plus 5 plus 6. That's all I've done. Exactly that. Right? Okay. So I'm just going to rewrite this right here as this intersection. And now that I've done that, right, okay, so basically I know that this thing right here is equal to this. And the next step I'm going to do is show that this right here is equal to the top line. Okay, remember what I want to show is this gold thing equals blue times green. I've just turned gold thing and turned it into this. And now I'm going to observe the following. That if I take this right here, I can break this into, I can use just the normal definition 14.1, the same old 2-event product rule, and say, oh, well, that's just the probability of an given the intersection of all these events times the probability of this event. Because remember, the intersection of a bunch of events is itself just another event. So you can just imagine this thing again is called Q. So probability of an given Q times the probability of Q. Okay? So we're getting close here. Now all we got to do is recognize that this probability, like the probability of the intersection of the first n minus 1 events, is just this. How do I know this? How can I do this black to blue substitution? That's the inductive hypothesis. Here it is. It says so. I assumed it's true. So that means I'm going to take this and replace it with this big old block of blue. And that's exactly what I wanted to show at the top line. Okay. If you're not totally happy with this proof, it's actually really simple. You can just take an example for like, I don't know, pick an arbitrary n like 4, and then show that it also works for 5. And if you do that, it's the exact same pattern. So if you're a little overwhelmed by the algebra, try it for the n equals 4 case and you'll be fine. Yeah?
Why is it in that
Mm-hmm.
For it,
Yep.
why are we taking the a(n-1) event and not the a event?
Let's see. We want to show.
I think there's a typo.
Where's the? Oh, this right here.
Yeah.
Yeah, that's a typo. See, okay, that one I was not part of my desync. That's just something I missed last year. Thank you. Okay, the green helped, right? You're able to spot the typo easy. Okay, good. Thank you. And let's fix it on the other slides to avoid confusing ourselves next semester. No one caught that last time. What does that mean? It means you guys are experts at the math. Good job. Okay, cool. Anything else? Okay. All right, great. Okay, so that's the product rule. So that tells us how to deal with intersections of events. Let's talk about unions of events. This is a very rich topic. We're going to do a lot with this, both today and much later when we talk about concentration inequalities. So let's, as an example, suppose we roll 3, 4 fair-sided dice. Okay, normal kind of grounded thing we want to do. And let's say we win if we get at least 1 4. Okay, so I'm going to claim, just for a moment, that the probability of winning is 75%. Because, I mean, I have 3 different ways to win, so I get 3 times a quarter, because I have a 1/4 chance each time, a 3/4 chance of winning. Is this claim correct? No, why?
You're overcounting if you get.
Yeah, I'm overcounting.
You're overcounting if you get like 4 multiple times.
Totally. This is not good, right? Imagine we roll 4 fair-sided dice. Well, then I'd say the chance of winning, stop doing that. It's okay. It's okay. I promise. There's a YouTube link. Deal. So if this argument worked, you could say, well, if I roll 4 dice, I'm always going to win, because then I get 4 chances. And if I roll 6 dice, I have a 150% chance of winning. That's great. Like, what could be better? So this does not work, okay? We know why. We saw this in the principle of inclusion-exclusion lecture. And so we're going to think about this. We already know how to use the principle of inclusion-exclusion. This will be a little bit of a review of that idea. But I'm just going to walk through. I'm going to give a visual example, make sure we're really grounded in understanding this, okay? So the issue is that our events are not disjoint. There's overlap. This is the sample space for 3 4-sided die rolls. Don't need this word die here. A1 is the event where the first die is 4. Okay. A2 is the event where the second die is 4. And here we notice that some of the events occur, or some of the outcomes are in both events. Right? An event is just a subset of the sample space. And what happens is that if we just add the 2 probabilities together of A1 and A2, it doesn't work because we're double counting these points. And it gets even worse when we add the third event. Okay? How do we express this compactly in algebra? The way we showed this before is we said that the size of the set that is formed by unioning A1 through AN is this sum with alternating signs. And each of the different sums, each of the little summons is intersect sum. And remember that when I pick K, 1, it's each of the individual terms. 2, it's each of the pairwise. 3, it's each of the 3-way. 4, each of the 4-way, and so forth. What the notes do is they have this other notation, which is exactly the same thing as what I did in lecture. Basically, you think about this as this whole thing is all of the K-way intersections. So if K is 1, it's just the sum of the individual probabilities. If it's 2, it's all the pairs and so forth. And I am going to unroll this as an example in a moment. But this is the compact way to represent this idea of how we count the size of sets, how we count the size of the union of several sets. Okay? We've already seen that before. Now, because probabilities, the way we go from size of sets to probabilities is all we did is we have a probability function. We have a sample space and now a probability function. And so on a uniform probability space, the probability of the union of all of these different events will simply be the size of that union over the size of the entire sample space. So all I'm saying basically is like counting the size of sets is the same thing as summing of probabilities. Okay? So this right here is what we saw in the previous lecture. This is the slightly different version for today, okay, which is I want to know the probability of the union of several events. What's the chance that I win the dice game? Well, all I need to do is add up the probabilities of the individual events that comprise winning, okay, intersected appropriately. So what does that look like if I take this big ugly expression, which previously we called intersect sum, and I do it for my dice game? Okay, what do I get? Well, the probability of the union of 3 events is the sum of the lowest order, the singletons, intersect sum sub 1. And then I subtract out each of the pairwises, and then I add back in the 3-way intersection. So all of this algebra right here, it looks really big, but it's simply this idea. Okay? What does that actually mean, though? Okay, I get it. I remember this. Well, let me see. I'm going to go all the way to the bottom just for once and show you what this looks like with algebra and then visually. Okay, so first, the probability of getting a 4 is going to be a quarter for each of these. Question for you. What's the chance that we get a 4 on 1 and 2? 1/16. Someone else has to answer, though, today. So that's your last one for now. But I'll rope you back in. Not a chastisement, but I want to make sure I get these guys active, because I don't want them getting too sleepy. All right. So this one's going to be 1/16. They're all 1/16, okay? And then what's the chance that all 3 dice come up? 1/64. Yeah, there we go. Okay. 1/64. So we add that one back in, okay? All right, so that'll be the chance that we win. So it's not the naive one where we just add them all together. It's not where we subtract the pairs. It's now we got to add back in the last one. Okay? So the overall probability, if we apply the principle of inclusion-exclusion, is just going to be 37/64. This all worked because the probability of the intersection of the union... Okay, union... Whatever, okay, I'll fix it. Oh, no, actually, that's right. It was correct. Okay, why am I messing with that? I'm going back in. This all works because the probability of any of the individual intersections is just the product of the individual probabilities. So, for example, if I'm intersecting 1 and 2, I got 1/16 for the case where we had 1/4 and 1/4. Okay? All right, visually what was happening there, okay? You've already seen this, but I just want to show it, just make it very clear that this is exactly what's going on, is that in my sample space, these are all the sample points. When we added A1, A2, and A3, we got 48/64, 75%. That's too high. The reason that happened, on the right I have a diagram just showing how many times we counted each point. So why is this one 3? Because it's at the intersection of the red, the blue, and the yellow. Okay, so if you only considered adding up these numbers here, you get an upper bound. The probability is definitely less than 48/64, but it's too big. Then what we do is we get rid of all of the events, all of the outcomes that are at the intersection of the events A1 and A2. So we cross these out, and so these are only counted once. This is counted twice. Okay. Then we subtract out all the points that are at the intersection of blue and yellow, so these ones all get crossed out. And then we cross out all the ones that are where? Try and imagine. Okay, that's where they are. They're on the bottom right corner, so all the things that are red and yellow. And at that point, we've gotten everything to count once, except there's one problem, which is this one. We originally counted it 3 times, and we crossed it out 3 times. So we have to add that one back. Okay? So if inclusion-exclusion was a little fuzzy before, that's all you're doing, really. Yeah?
But we can also do like 1 minus the exclusion of all of them.
You could. I'll talk about that in a little bit. Yeah, so I'm not going to say that out loud, but that's another way to compute this that's easier. Yeah. Okay? So that gives us the union of events just using the principle of inclusion-exclusion. There's nothing new here that was not in lecture 13 other than the symbol P for probability. Okay? All right. So mathematically then, we can use this principle to compute the probability of unions. Sorry. Okay. All right. Again, this is the downside of slides, is they're not perfect. You look silly, and there's mistakes. But practically, this becomes hard to use, even for fairly modest sizes of n, where that's the number of events that I'm unioning together. So let's say I have 100 events, and I want to compute the probability of their union. Well, then we need to, if we want the exact answer, we might need to add or subtract a bunch of pairwise, 3-way, 4-way, 5-way, 6-way, and so forth intersections. There's a whole lot of those. Okay? For the counting lecture, we actually know there's 2 to the n minus 1 such terms, because if we add up all of the different ways of selecting, all of the singletons, all of the pairs, all of the trios, and all of the everythings, you get 2 to the n minus 1. Okay, so that's a lot. And 2 to the 100 is just too long to wait. So if I have 100 events, I don't want to have to compute 2 to the 100 terms. That's going to take too long. Now, there are a couple of, you had an example of one way we could avoid all the trouble. There's actually an even simpler case. If we're lucky enough that our events are mutually exclusive, that is, that their intersections are 0, then all those intersections are 0. We don't have to add them. We don't have to do anything with them, right? So we just sum the probabilities of the individual events if the events do not overlap. Okay? We've actually used that before. For example, if we're computing the probability of a flush, if these are all the different flushes, well, you can't get a spades flush and a heart flush at the same time, right? These events are totally disjoint, and that none of the spade flushes overlap any of the heart flushes. So what we can do is just say the probability of the union of these flushes, this come out kind of ugly, is just going to be the sum of the individual probabilities. You use that on homework 8. So if the events are totally disjoint, have no overlap whatsoever, you don't have to worry about it because all the intersections are empty. Okay? Another possibility is if the events do have overlap, but they're independent, like we did with dice rolls. Okay? We tried to win by getting a 4 on any of 3 dices. There's a shortcut, which you noted, which is that the probability of the union is just 1 minus the probability of the intersection of the opposite of the events. Now, this isn't actually mentioned in the notes. It's just something I guess you're supposed to think about, which you did. And so an example here, if we were to actually, if these events are all independent, then we can very easily just take these probabilities and separate them out, right? So if we have the probability of the intersection of many events, as we saw in the product rule part of today's lecture, we can just separate them out. There's no need to actually write out a product rule thing here. Each of these things is totally independent, so we can just take them into their separate probabilities. So for example, with dice, which we just showed was, what was it again? 37/64, something like that. What we would do is we could say, AI is the event. We get a 4 on the ith roll of a 4-sided die. Are these events disjoint? No, they're not disjoint. We just saw, like, there are red points and blue points and yellow points that were overlapping. Oh, sorry, there were red, blue, and yellow events that were, the events were overlapping. There's some sample points that were in multiple events. But they are independent, right? Like whether I get a 4 on the first die is independent of whether I get it on the second die. So what I could do is say the probability that I get any 4s is the same thing as 1 minus the probability that I don't get any 4s, right? Makes sense? So if probability of getting any 4s is 1 minus probability of getting all not 4s. Since each of these events is independent, we can just multiply their probabilities directly. So it's 1 minus 3/4 times 3/4 times 3/4, which is 1 minus 27/64, which is 37/64. Okay? So for events which are disjoint, the principle of inclusion-exclusion just degenerates into summing the probabilities and is easy. If your events are overlapping, they're not disjoint, but they're independent, well, then you can just go to the complement. And that's basically what we did with the birthday paradox. And then you have a relatively easy computation. And sometimes you don't get those tricks, right? Sometimes you don't have either of those tricks. They are not independent and they are not disjoint. In that case, you're really stuck. You can't use any tricks and you end up with a big complicated sum. Well, sort of. Let's say you actually don't care very much about the exact probability. I just want to get a rough estimate. One note I'll make is that this bar shouldn't exist. There should not be bars around this. Sorry, I thought I fixed all that. But if you're very carefully looking at a notation, there should not be lines around that. But let's suppose that we pick just another number like 4. And then we say, I'm going to stop using the principle of inclusion-exclusion at 4 because I'm tired. I don't want to go out to all the 100 different possible number of different items I'm going to be combining if I'm doing n equals 100. I'm just going to stop at 4. I'm going to consider the individual probabilities, the pairs, the trios, the quartos, and that's it, let's say. Well, we know that, or we kind of know, actually we haven't proven this, but if we pick an odd n to stop on, then whatever we get is an overestimate. So for example, if we just only do ns equals 1, that's what we did with the dice game. We had 3/4. And 3/4 was not the chance of winning. That was an overestimate, but it's an upper bound. And if we ever stop on an even, the computed value that we get will be an underestimate of the true probability. And so for our dice, remember, as I just said, if we pick ns equals 1, we got an overestimate of 3/4. If we were to stop at 2, where we take these and then we subtract off the pairs, we get a small underestimate. And then as we go, as we add more and more terms, we get a better and better estimate. And you could stop wherever you want. Is there a question? Yeah.
Is there
Mm-hmm. Right. So if you have a situation where the intersections don't exist beyond 3, yeah, then the principle of inclusion-exclusion, it will degenerate, and this will no longer be true. So you're right. There is a caveat here, which is this is assuming there's still more terms that are non-zero beyond. Yeah, okay. That's just a good small technical point. Okay. Yeah.
Kind of a notational question.
Yes.
Explain in the right more summation.
This thing here?
Yeah.
Yeah.
Explain what that notation means.
Sure. This is saying I want to consider all the sets, all the subsets of 1 through n, such that the size of the subset I'm forming has cardinality k. So for example, if k is 3, that's saying I want to pick like 1, 3, and 5, 1, 3, and 8, 1, 3, and 9, and so forth. So it's all the k-wise combination, all the subsets of the integers 1 through n of cardinality k. Yeah. Yes, right. Yeah, it's the summation form of intersect sum. And then the slight technical error I made when I typeset this is these should not have bars. It's the probability of the intersection of the events, not the probability of the cardinality of the events. Yeah, doesn't make sense. Yeah. But you can also just pretend this as intersect sum. Oops. Okay. Okay. Let that happen. All right. Okay. Now, there's one very special case, which is the laziest case, that's great for us, where we're just going to pick ns equals 1. I'm only going to consider the individual probabilities, and this is sometimes called the union bound, or I've also seen this called Boole's inequality, which basically says, well, I mean, yeah, the probability of winning the dice game isn't 75%, but it's definitely less than or equal to 75%. So the probability of the union of a bunch of events is just less than or equal to the probability of the individual events. Is this practically useful? Well, we'll see actually it is in the little second part of this lecture. And then later, actually, we're going to use this in a more abstract way. Instead of applying it to specific probability problems, we'll use this to derive very clever bounds on what kind of probabilities are even possible. This happens in maybe 3 weeks or so for any possible distributions. I haven't told you what a distribution is yet. Okay. Now, I'm not going to prove this thing. It's given as an exercise. If you look at the end of the notes, there is a proof that's straightforward enough that the notes don't even tell you. They say, go for it. And you can actually go further and prove that as you increase NS, you switch between over to under estimates, and that it always gets monotonically better. This is beyond the scope of what I want to talk about in 70. It's interesting in mathematics, the one thing I always, the thing that I never really resonated with me spiritually were like convergence proofs. So if you're an applied mathematician, I apologize for this, but somehow knowing like the exact rate that something converges like doesn't usually get my gears going, though I do have one today that's kind of fun. Okay. So summarizing the end of notes 14, what we got is 3 distinct topics. The first thing was we defined the conditional probabilities of outcomes and events. We got definition 14.1 out of that. That was great, right? We got the thing that we used, that the probability of an intersection is the probability of one thing times the probability of the other thing given the first thing. I don't know. I mean, maybe that's useful for me to say out loud. That was the first big thing we got. The second thing we got was Bayesian inference, which gave us Bayes' rule and the total probability rule. And then we talked about combinations of events. If the events are independent, things are relatively easy. If we have intersections of non-independent events, then we could use the product rule. So that was like our flush example. And if we have unions of non-independent events, we can use the principle of inclusion-exclusion. But the problem is it blows up exponentially in the number of different events we're considering. If the events are disjoint, we actually don't get blow up. We just add the probabilities. If the events are independent, then we avoid the blow up. We can avoid the blow up by doing the trick you mentioned earlier, which is just consider the complements of the events. And then if we have other unions, in principle, we actually have to compute it. But in practice, we could truncate if we want an approximation, like the union bound. If we ignore everything above pairwise, then that's called the union. Okay? All right. I do want to note something about homework 8, which maybe you all finished, which is to note that when you're solving a problem, different problems can be radically different and different framings of a problem can be radically different in difficulty. So for example, in homework 8, there's a question which says, how do you compute the probability that you draw at least one ace? And maybe you tried it 1 or 2 different ways. Maybe you got a little stuck. Now that you have the language of events, you can reflect on maybe why some of the techniques were harder than others. So for example, you could think about this as the probability of the union of drawing one ace or two aces or three aces or four aces. Or you could think about it as the probability of drawing the ace of hearts or the ace of diamonds or the ace of clubs or the ace of spades. Both of these work, but the first approach is easier, and that's because those events are disjoint. If you draw four aces, you cannot also have drawn two aces. But if you draw, they've set up a trap for me. If I've drawn the ace of hearts, I might have also drawn the ace of diamonds. So you can do it this way, and maybe some of you attempted this on homework 8, and then you're like, wait, do I need to use inclusion-exclusion? And you could have maybe gotten it. So be aware that framing your problem appropriately, setting up your sum basically appropriately, can make the difference between pain and not pain. And one of the things that I really recommend to get good at this class is to discuss with other people how you solve the problems. Because it may be that you did it this way, and you got the right answer, but you spent a lot more effort than somebody who just did it the more straightforward way. Okay? All right. Okay, let's do our next lecture. This is a shorter one, which is good, because it's not only the part of the time. So I do want to note here that I'm gone a little rogue because I found the notes maddening last semester, because we had these weeks where like note 19 happened across 4 different lectures. And I don't know about you, but the notes I find dense. So the idea is a student who's new to CS70 trying to look at each note and be like, but which part is with this lecture? I don't know, it's too much. So what I'm doing is I'm just gonna make a new set of notes. It's a remix of the old ones. Change things a little bit. I try not to mess with the stuff too much though, because it's not my class. I don't own it like 621B. But there's gonna be 1 set of notes per lecture, and maybe they'll stick with this in the future. So I'll try and have them done 5 days in advance. Notes for lecture 18, which will be Thursday, are basically there, and 17 are up already. Okay, but if you notice the notes changed numbers recently, that's why. Okay. So note 17 is kind of a bonus topic in the class. It's nothing new. It's just practice with the notes 14 material. And by the way, there's no notes 15 and 16 now. They have been eliminated because I want the note numbers to match the lecture numbers. So it goes. Maybe I'll make some secret notes for you. And note 17 is basically 3 things. 1, it looks at the birthday paradox. So if you throw a bunch of balls, what's the chance that 2 of them land in the same bin? It looks at the coupon collector problem, which is how many times do you need to throw a ball before you have a desired chance of having 1 ball in each bin? And load balancing, which is if I throw M balls in N bins, what's the smallest K I can pick so that there's a 50% chance that no bin has more than K items? And this one I kind of find hard to parse, but the basic idea is imagine I mail 350 million pieces of junk mail to everybody in the whole country, to 350 million different addresses, assuming everybody lives by themselves for some reason. Well, then I can say that with probability 50%, nobody gets more than 12 junk mail. So if I just spray the junk mail everywhere, it's no more than a 50% chance you get 12 pieces. Okay, I'm going to cover the first problems in lecture. I mean, there's multiple perspectives on this first one. And then there's extra slides that help decompress, or if you're finding the notes hard to read, I have some extra slides, but there's just not enough time in lecture. And also, I should note that there's never any homework or discussion problem on this notes. So I think of it as a way to practice note 14 concepts, I guess this should really say. Okay, we're going to fix it. Okay. All right, so let's jump in and do the birthday paradox. Okay, so this is going to be a little bit of review. Maybe this is good for you, maybe it's not. But I'm just going to review what we know. So we've already seen this collision problem, the birthday paradox. And we're going to start with just the review, and then we're going to do something new involving union bounds. So if we have 365 different birthdays, we had that question. How many do you need before we have a 50% chance where 2 people have the same birthday? Now, I should note, this is a real thing. It's not just birthdays. For example, git commits. Like when you make a git commit, it generates some giant hash value, some sequence of digits. This is just a sequence of numbers. It is computed by taking all of the information about your commit, like all the code or whatever else, and then spitting out like a number. Okay? And ideally, you don't have 2 commits with the same hash, because if you look at the history of git commits, they're all supposed to have a unique number identifier. Okay? So this would be the equivalent of there's so many different hash values, so many different birthdays for your commit. And you want to avoid collisions where 2 different commits have the same birthday, so to speak. Another, I don't know if you've ever downloaded files from the internet and you check a SHA hash to see if you have the right file. Ideally, you want to avoid a situation where I can put out like a version of Linux, but it's not actually Linux, it's my own malware. And the way we try to prevent that is whoever publishes Linux says, hey, here's the hash of all of the operating system. It should ideally be really hard for you to make a poisoned version of the operating system and then be able to present the same SHA hash. Okay? Or RFID tags. So RFID tags have a 96-bit identifier. If I release a product, I just pick a random 96-bit number. Ideally, it should not be the same as your, I don't know, stuffed animals or cans of beans or whatever that you want to put out there. Okay? So in all these cases, we don't want collisions. And this math could be used to say, okay, well, how big should the space be if I think I'm going to have 100 trillion users doing this at some point? What do I need to do to feel pretty good we're not going to end up with birthday collisions? Okay? So we can model the birthday paradox as balls and bends. In fact, this whole notes is about balls and bends, 3 different ways of thinking about it. So if we have 6 bends and we throw 5 balls, one possible outcome is the following. So we have 4 in bend 2, 2 in bend 3, 3 in bend 5, 1 in bend 5, 5 in bend 5. So those 3 different people, so to speak, have the same birthday. All these balls have collided. Okay. Now we already know how to solve this. So again, this is just review. How did we do it? Well, we defined A as the event where 2 or more of the balls land in the same bin. You can already feel the union bound coming somewhere, okay? Let's say omega is all the possible ball throws considering order. Well, we said if we had 365 balls, for example, then the probability of getting a collision would be the cardinality of the set A over 365 to the m. And in a previous lecture, we said, I don't know how to figure out the cardinality of A. It's too hard. So what did I do instead? Anyone remember? A naught. Yeah, I did bar A, and I said, okay, well, I'm going to reframe it as 1, like the probability of A, as 1 minus the probability of A bar. A bar, it turns out, matched one of our counting problems exactly. We could just say that A bar is just the product of 365 times 364 down to 365 minus n plus 1. Okay, this is all something we did before, and we got this function. This is the probability that I get a collision if I throw m balls into 365 bends. So it goes up. Once I get to 23, we cross the 50% mark, and it keeps going up. And that's our closed form, or that's our simple expression that can plug in an m, and I will get the answer here. Any questions about that whole thing? I will note that in that previous lecture, m was used for what we call n here, and n was used for what we call m here. So if your brain short circuits, that's why. Okay, but m is always the number of draws or balls today, so number of people. Yeah.
So when it says you get n equals 365 balls,
If your brain short circuits, we have 3 bends. Jeez. There's like a neuron in my head that can't do this. Okay, there we go. Yeah, we fixed the number of bends in this case in advance, and we're looking at the as m grows. Yeah. Say again? Good? I didn't hear the last thing you said. Okay, good. Okay. Okay, let's fix bends again. If we have n bends instead of 365, then the expression is just the same. So all I've done is I've gone from 365 to n. We get this probability. Okay, we don't have a nice curve anymore because n is, now it's a function of 2 variables, so I can't just plot this easily. I could do a 2D plot, wouldn't be interesting. Another form that's used in note 17 is slightly different. So that's just the expression we just showed in a previous lecture. We could rewrite this by separating out all these different terms. So n over n times n minus 1 over n and so forth. There's m of these things. So you could write it that way, and then you can divide out the n's, and you can get 1 minus 1 over n times 1 minus 2 over n and so forth. Okay? So this is another way to write this whole thing, if you so choose. All right. Yeah. Yeah.
There's a typo.
No.
With that n times n minus 1 thing.
There is?
No, a few slides before.
Oh, for you forward. Okay. Can we fix it later?
Yeah, that n minus 1 has no parentheses, so it's n times n. So it's n squared minus 1 times put it all the way back.
N times n minus 1. Oh, there's no parentheses here, you mean?
Yeah.
Oh, that's okay. We know what's going on here. But I'll give you that one. Okay, here you go. I'll put it up here. I'll just... Okay. All right. Thank you. All right. Let's talk about the product rule. So we could also solve this problem. So I'm just going to, this is about lecture 14. We learned some tricks. Let's use them. Okay. So how can we use the product rule here? Well, let's suppose we're going to define AI. We're going to try and be clever. So this is like whenever you're doing homework A. You're trying to define, here's the thing I want. What are its components? Okay, I want to know what's the chance to get an ace. So maybe I get 1 ace, 2 ace, 3 ace, or 4 ace. Or maybe what's the chance to get ace of hearts, ace of diamonds, ace of spades, ace of clubs. This is that job. So I'm going to define the sub-events that comprise the big event, however I want. And my idea is that A sub I is going to be the event where the ith ball lands in a different place than the previous balls. That's the event I'm going to define. And if once I make that choice, that's the smart part, then the product rule makes it very easy to compute the birthday paradox. Okay? So how am I going to do this if I define these events? How do I know these events are going to work? I don't know, gut feeling. Okay, let's try it. Okay, so if we do this, if we define the events this way, how does it go? Okay, so we know that the probability that we don't get a collision is going to be the probability of the intersection of all of these, because it says that A1 landed in its own space, and A2 landed in its own space, and A3, or sorry, I was saying A, I should say, sorry, ball 1, sorry, once more. What's the probability that ball 1 lands in its own space, ball 2 lands in its own space, and ball 3 lands in its own space, and so forth? That's what we got here. If all of those things are true, then there's no collisions, because they all have their own home. Okay? If I write that out as the product rule, which we proved earlier, it looks like this. And now all we got to do is substitute in all of these terms. So let's do them. Okay? What is the probability that the first ball gets its own home? 1. Yeah. It's not going to collide. It's free real estate, right? Okay. Second ball. What's the chance if I have n homes that the second ball gets its own home if the first one already had its own home?
1 over n.
I heard 1 and 1 over n. Huh? Say again? Yeah, 1 over n. Oh, wait, sorry. N minus 1 over n. Sorry, n minus 1 over n. Wait, is that right? Yes, right, yeah, because that's the choices. You have 100 ball bends, and 99 of them are good. Okay? Okay, now 2 of the homes are occupied, so what's the chance that the next ball gets its own home? N minus 2 over n and so forth, all the way up to n minus m plus 1. Yeah?
For that, the probability of what if 2 are occupied,
Okay. So these are these individual probabilities. So how do I get the probability of no collision given all these numbers here? Yeah, just multiply them together. So I multiply them all together. So 1 times n minus 1 over n times n minus 2 over n, and so forth up to this. Oh, hey, it's that same expression. So that's another way of solving this problem that didn't involve all of that rigmarole. Okay? So this is the same answer we got earlier, just without having to count set sizes. Checking on my battery. Okay, everything's good. All right. I forgot my charger today. Okay? So that was just a demonstration that, hey, isn't the product rule cool? Okay. All right, let's do some union bounding. I'm going to look right into the belly of the beast. Okay, there's that old, like, don't gaze into the abyss, lest the abyss gaze back into you type of thing. Well, I'm doing it. In the previous, or in a few lectures ago, when we did birthday paradox, I said, I don't know how to do A. Like, here are some examples from A. What is A? These are all the ways of drawing birthdays such that there are collisions. Okay, well, that seems like, how would I even do that? Okay. I gave up before, but today we're going to actually figure it out. That's what we're going to do. Okay. So this time, I need to frame A in terms of some separate events. So with A bar, it was A1 was the chance that the first ball had its own home. A2 was the chance the second ball had its own home, and so forth up to A bar, up to all the events. With A, we need something else a little different. So we thought about it as a union, like before I show it on the screen. How might you decompose having a collision into a union of events? Thoughts? Yeah?
that the first ball is in a certain spot and the second ball is in a certain spot.
Right. So that's one possible event. The first and second ball share a spot. Give me another event that's in A. That's not that one. over here. So you suggested one outcome that's in, sorry, you suggested one outcome, which would be that ball 1 and ball 2 are in the same spot. Another one? 1 and 3, exactly. 1 and 4 and so forth. And there's many different ways that 1 and 2 could be in the same spot. And 1 and 3 could be in the same spot. So I'll define those all as events, which I'll call C. It's the event where the ith pair of balls collide. Okay? So I'm going to number them like this. So C1 is going to be that 1 and 2 collide. C2 is that 1 and 3 collide, all the way up to C10. If I only have here, the reason I have 10 here is I'm imagining that if I had 5 different balls, there's 10 different pairs, right? Just M choose 2. There's 2 different ways to take pairs, and we end up with, in this case, C1, C2, up through C10. Okay. Notice this is not the number 45. This is saying that balls 4 and 5 are colliding. Okay. Does this make sense? So if I have 5 balls, I have 10 different events that I count as collisions. And so then the probability I get any collision will just be the probability of the union of these different events I've defined. So let's think more carefully about these events and start doing some of those little Yalki questions in a moment. So let's suppose as my first one, if, this one you don't have to do anything to submit, but if we have these as my 5 balls and I've defined C1 through C10 appropriately, which of the events are true? Which collisions occur? What numbers? Is it C1? Is it C2? Think about that for just a sec. This is C1, this is C2, C3. Okay, did C2 happen? Yeah, sure did. Okay, C2, C4, and C9 all happen. Okay, so we're 3 different collisions from our list of possible collisions. Is this the only way to frame this collision problem? No, not at all. But it's just the one I picked. Okay, so if you have in your head, like, couldn't you? Yes, probably. All right. So first question, that's actually one of these of the day, is if A is the probability that any collision occurs, how do we write A in terms of those events? And let's see what this one looks like. Uh-oh, I'm out of minutes. Oh, no, I'm not. Okay. Okay, how's it looking? Crossing my fingers. And I'm crossing my fingers that it's actually showing up and showing what I wanted to say. Okay. Bummer. Getting better at 70, but still got a ways to go. Okay. All right. So I don't know what answers you had on your thing. So hopefully they made sense. So what it should be is the union of all the different collision events and how many of them there's M choose 2. Okay. All right, next up. Are these events independent? What do you think? Next question. This is a little gauntlet of these questions, concentrated at once. Okay, now maybe it'll work. Okay. So we're at about 60%. People think the answer is no. It's a little subtle. Interesting that we're about half and half. All right. So it turns out they're not independent. Why? Okay, a lot of you were wrong about this, but maybe 40% of you are wrong. So example is if 1 and 2 collide and 2 and 3 collide, then you know that 1 and 3 also collide. Okay? So the probability of, if you know the information that 1 and 2 and 2 and 3 have collided, then you also know that 1 and 3 collide. So they're not independent. Okay? Now, if they were independent, then we would have an easier time, as we know from the previous lecture. But because they're not independent, we have to do something a little fancier. Okay, so a vaguer question. Could we just use the principle of inclusion-exclusion on a practical basis? Like, we know it'll work. It's a union of events. But would we run into some trouble? This is less... I don't think this question's as good as the previous one, but... Question. Okay, let's see. Oh, we got some comments. Yeah. Okay, this one we're like dead middle, like 50%. We're guessing. Okay, so it goes. So it turns out in this case, I'm going to claim that it's not super practical for modestly sized m's because you would end up with a whole lot of terms. I said earlier, if you have n different events, you have 2 to the n different terms, or 2 to the n minus 1. In this case, we have roughly m squared terms, right? If we have C1 through C sub m choose 2. So that means I got 2 to the m choose 2, and m choose 2 is theta m squared, if you know what theta m squared means. Okay. Point being, there's a whole lot of terms. If you were to actually write out these terms for just a small number of different balls, you have a lot of different pairwise combinations, and then you need to consider all the possible inclusion-exclusion combinations of those. Okay. Now, as I discussed, though, and this is why we're going to run into trouble. So in the previous lecture, I said, yeah, no problem. Use the principle of inclusion-exclusion. And yeah, maybe you have a bunch of terms, but if they're disjoint or independent, then you're all good. But this is one of those cases where I can't use either of my tricks. They are not disjoint, and they are not independent, and therefore you are really stuck having to do it all. So now we're going to use the final trick of the previous lecture, which is, well, we're just going to ignore all that stuff. Okay? So why are we bothering to do CS70 if we're just going to throw away all that stuff? Well, we'll see. I mean, like, we'll get something that's useful. Okay? So I'm just going to throw away all of the pairwise terms and all the three-way and everything, and I'm just going to say, let's add up the individual probabilities and see what happens. So what is it going to be? Okay, so this is the union bound. This is going to be an upper bound for the probability that we get a collision. We're going to ignore the fact that, yes, we need to subtract all the pairwise and add back all the three-way and so forth. So question for you, if we're just adding up m choose 2 of these things, the thing we need to know, we know m choose 2 already, like it's m choose 2. What's the probability of any particular collision? So try and do this one. So what's the probability, if you want to just think about a specific example, what's the probability that the first 2 balls collide? That's good enough. Any pair is fine. They're all the same. And of course, there we go. Okay. All right, I'm going to give it away. Okay, so what is that probability? So what's the chance that any particular pair of balls collides? Well, let's say that the position of the first ball is, I don't know, bin K, like whatever that is, like 38. The chance that the second ball also lands there, so the first one lands, boop, and now you throw the second one. What's the chance the second one lands in the same place? Well, it had a 1 in n chance, so it's 1 over n. Okay? Because it doesn't really matter exactly where they collided, it's just that they collided anywhere. Okay? Yeah, it's basically if you roll a 20-sided die twice, what's the chance you get the same number twice, or whatever? Okay, so what's the, yeah? That would be the chance that they both collide in the first bin. Yeah. So that would be, you have a specific bin in mind. There'd be a 1 in n chance that the first one lands in the bin you want, and then a 1 in n chance again that you land in the same bin again. But if you don't care which bin they're colliding in, the first roll is kind of irrelevant. It just sets the stage. So I roll a 20-sided die and I get 17. Okay, great. I roll it again. What's the chance that it matches the 17? 1 in 20. Does that make sense? So think of the first roll as just kind of a throwaway. Yeah. So then what's the union bound? If each of these individual probabilities is 1 over n, and there's m choose 2 of them, the union bound is just going to be 1 over n times m choose 2. Why? Because there's m choose 2 of these. Why are there m choose 2? Because that's how many collisions there are. 1 and 2 could collide, or 1 and 3 collide, or 1 and 4 could collide, or 1 and 5 could collide, and so forth. Okay? So this gives us the union bound. We know that this is true. Whatever the actual probability of a collision is, we know that it is less than or equal to this right here. Okay? So that is, I can actually substitute in what is m choose 2? Well, that's m times m minus 1 over 2. And then I'm just putting the n in the denominator. I can bound that above just slightly by saying, okay, well, it's called m squared. And what this tells us is that the probability we get a collision is guaranteed to be less than m squared over 2m. Okay? What is this mysterious expression? Well, it's an upper bound on what the chances could be. It's an overestimate. And so let's play with it a little bit. We've just shown that if we want to do the birthday paradox, m squared over 2n is informative. It tells us what the chance of a collision is. It's definitely less than this. Okay? So in other words, if there's 365 bins, and we have m balls that we throw into them, the probability of a collision is less than m squared over 730. So I throw 0 balls, the probability is going to be, well, less than or equal to, I guess I should say. It's going to be less than or equal to 0. If I pick 1 ball, it's going to be less than or equal to 1 over 730. If I've only thrown 1 ball, what's the actual probability we had a collision? 0, okay. But this is an upper bound. Okay, so that's fine. Okay. Let's say we want to know, then if we just trust this equation and we say, well, I know it's an upper bound, what does it suggest about how many balls I can throw before we run into trouble? Well, we can compute the m by just saying, okay, well, what value do I need to plug in for m to get to 1/2? So m squared over 730 equals 1/2. Okay, well, then I multiply this both sides by 730. I compute the square root, and I get root 365. Obviously, this generalizes to other n's. And the basic idea is that a very rough estimate based on the union bound for the number of balls you need to throw is just the square root of the number of bins that exist. In this case, 19.1. So basically, if we throw less than 19.1 balls, we're guaranteed to have a less than 50% chance of a collision. Okay? It's not that we won't have a collision, it's just that we're guaranteed, whatever the true probability is, that's that complicated expression, this is a simpler expression that will work. This plot, I think, helps elucidate. This is the true probability of getting a collision. The one that we derived in the previous lecture, the one that we re-derived using the product rule, and this is the union bound, which is very easy. It's very lazy. All it does is it sums the probability of the individual collisions. Right? So here's what it looks like. It goes up like so, and you'll notice it hits 1 at some finite or at some relatively small number of balls because it diverges. It's an upper bound. And then once you get past this point, I mean, it's not a very useful bound at some point, but down here, it's not bad. It says, when do you hit 50% with a union bound? I mean, it's a little early. 19's a little conservative. The true number was 23 or 22, depending on what you want to say, what you mean by the critical threshold, but it works. Makes sense? So it's an upper bound. And sometimes, I mean, this bottom curve may be inaccessible to you. It may be some monstrous thing you cannot compute. And this right here, you just want a guarantee. You don't really care about the exact probability. You just want to have a safe guarantee, and you say, I'm not going to do more than 19. I'm in good shape. Any questions about this? So to summarize, basically, we did a lot of effort to get this blue line, and we did very little effort to get the red line. That's really what it boils down to. The red line's not as good, but we didn't have to work hard to get it. Okay? All right. I got one more little trick for you then today, which is, could we do better? Can we get a tighter bound on this probability? Okay. The way we did this one is we looked into the abyss, and we said, I'm going to try and compute the probability of a collision, and I know it's hard. In fact, I know there's an exponential number of terms. I'm not going to get there with that approach, but I'm just going to cut off the top so many terms, and I'm going to use it as a bound. This other approach is a different flavor. Okay, so here's the other idea. Okay, so this is the union bound approach, which is gaze in the abyss and make an approximation of the abyss. That's what this was. The alternate approach, if let's say what I want to do is I want to find this number in a more nice way. Like, how did I actually pick this safety threshold? I actually found the blue curve, and then I tried out a bunch of m's, tried a bunch of different ball numbers, and then I found this one. But I don't want to do that. Okay, I want an expression that gives me the right answer. It's not a bound. It's not some rough bound, and I don't have to do a bunch of guess and check. Right? The reason I got this was guess and check. I plugged it into this big complicated expression. I want to do better. Okay? What I mean by that is, this is the probability we have no collisions. And if I just try a bunch of different m's, right, each one of them takes a bunch of computation time because I have to multiply out all this stuff. Well, depending on how you do it, you can do it faster, but I have to guess and check. If I use this expression, there's no closed form solution to just say, put a half on this side and solve for m. Just, you can't do it. Okay? But what I'm going to show is using techniques a little beyond the scope of the class. We can get a function that will give me the critical m from this ugly expression here, this product of a bunch of small numbers. Okay? So the guess and check approach, the way that you could do it, is I could say, okay, here's the true expression. I plug in a bunch of different m's, and I just wait, and then I get to this one, which is the last one that's above 50%. This one's too big. Okay, that's just what I've decided. I mean, you could decide, okay, I actually care about the first one on the other side of the line, but whatever, you get the idea. So once I get to 22, that's the last number I can use and still have a greater than 52% chance, or greater than 50% chance of no collisions. Okay? The union bound, by contrast, is, so this is the formula for having no collisions. The union bound is an upper bound on the probability that there is a collision. Okay, so in that case, this is the basic idea. It's a function that, notice that instead of the probabilities going down over time, they're going up. Why is it going up? So why does this one go down and this one goes up? Am I tiring you out? Yeah, I mean, this one's A bar and this one's A is kind of the short answer, right? This is the probability that there is a collision. So that should increase as you throw more balls. And of course, this being a bound, I mean, once you get up to m equals 50, this probability becomes nonsensical, but that's okay. All right. Okay, so what's this very last trick of the lecture? So we've basically seen two ways we could find the critical number of people, the max number of people that's safe, where we define safe as less than 50% chance of sharing birthdays, or if we're thinking about SHA hashes with Linux or whatever. So the exact answer approach is one way. You find the exact formula and you try a bunch of different m's, and you stop once you find the one you want. You can do that in log number of guesses, because you can binary search across the curve. The other approach was to use the union bound, and then we got this nice thing, which is just root in. The very last part of lecture, and I apologize that it's at the end of a lecture, but hey, if we go on a wild algebra journey, using a very clever trick that's out of scope for 70, we can give a formula that's better than root in, which is 1.177 root in. Okay, and why this number, I'll show you in a bit. But that's the spoiler. That's what we're going to get to go. Okay. All right. This is for my real applied math heads, what we're going to do here. So let's suppose I want to find the m that gives me some critical probability. What I'm going to do to make things nicer is the first thing I'm going to do is I'm going to take the logarithm of both sides, because the logarithm of a product is a sum of logs. That's the basic idea. It'll make my life easier. Okay? Doesn't matter what log base I pick. I pick natural logarithm because the notes picks natural logarithm, but you can pick log base 7 if you want. That's fine. Okay. Then we're going to make use of a handy fact that's going to make this expression tractable. If the thing inside the logarithm is small, right? If this thing right here is really small, if x is small, if x is small, then the natural logarithm of 1 minus x is going to be ever so slightly smaller than minus x. Let me show you by example. So if I take the natural logarithm of 1 minus 0.001, that right here is right here. So this, if I compute this number, it's negative 0.0010005, which is ever so slightly smaller than it's minus x. Okay, this symbol I'm using to mean just barely smaller. Do you believe me? Well, okay, I gave you an example. What about Desmos? Okay, I'm skipping the verification. They look pretty good. These are the two curves. This is the natural logarithm of 1 minus x. Here's minus x. And, I mean, they look pretty good. I mean, it's not perfect, but it looks pretty good close there. Or, if you still don't like that, we can talk about this in terms of Taylor series. If you haven't done calculus, I apologize, but you could do this. So you could remember, this is a little outside of 70. We're not going to use Taylor series at all in this class, but if you were to do this with natural logarithm of 1 minus x, so if we applied this procedure, well, what's the natural logarithm of 1 minus 0? That's the natural logarithm of 1. That's just 0. Okay, what's the derivative of natural logarithm of 1? What's the derivative of natural log of 1 minus x? 1 over 1 minus x, yada, yada. Plug in some numbers, you get this expression. I don't care. Point being, though, that this is the Taylor series expansion. And what do you notice at the front? Minus x. Okay? So this expression right here, natural logarithm of 1 minus x, is approximately this infinite series. And if I'm real lazy, I can just say, let's throw away all the terms over here. If we truncate after the minus x, this right here is going to be ever so slightly than minus x. And what's the error? Well, it's going to be less than all of this right here. The absolute error will be less than all that. So for example, if x is 1 over 100, then the error is going to be these very small numbers. Okay, that's if you care. That's a stronger justification for why we can say natural logarithm of 1 minus x is just slightly smaller than minus x for this example. Okay, so if you just trust me that that's possible, okay, then I can do the following. I can say that the natural logarithm of the probability there's no collision, like so, is just a little bit less than replacing all of these things with just the minus x, right? So minus 1 over n, minus 2 over n, minus 3 over n, and so forth. This is very clever, okay? Like I'm going to say this is beyond the scope of 70. This is not the kind of technique we expect you to use. It's all very nice. It's very applied math. It's very cool. And what it gets you is a nice expression. I'm going to do a little more algebra. Okay, I'm going to take this whole thing, and I'm going to say that's just minus 1 over n times the sum of the numbers here, 1 plus 2 plus 3, and so forth. That's just m times n minus 1 over 2. This is the sum of these first so many natural numbers, which is just minus m times n minus 1 over 2n. Feels kind of like the birthday paradox thing we did with the union bound. It's kind of similar. But the difference is that now it's that the natural logarithm of the probability that there's no collision is ever so slightly less than this expression. Okay? And this will work as long as these expressions here are small enough. Okay, are they small enough? We'd have to think harder, and we'll do some plots in a second to convince you. Okay. So once we're done, and this is the punchline of this very clever algebra journey, is if we exponentiate both sides, we get that the probability that there's no collision is less than, what? Like this is such a crazy expression. It's less than or equal to, just barely less than or equal to, e to the minus m times m minus 1 over 2n. Now this is the sort of thing that strikes fear, I think, into a lot of people who are like newish to math. And I should note that this is a trick that would be beyond me. If I got this after like a week of thinking about this, I would feel great because I'm not an applied mathematician. And I want you not to think that like only a genius could come up with this. Like anything, like math is just learning a bunch of tools. And an applied mathematician who is used to the idea of doing this kind of approximation, maybe they see it really quickly, and maybe for you it's hard. But please don't get the sense that there's some people that are math geniuses and some people are not. Just it doesn't match my sense of reality. There are some people who love math so much that they want to sit down and do it 6 hours a day, and maybe you don't, and that's fine. But it's not because your brain is wired wrong, just different interests. Okay, so this is something where if you were to come up with this maybe is like a cool result if you didn't already know all the supporting machinery. Okay, so we had this original expression up top, which you should feel comfortable deriving. That thing at the top, I feel like, should be within your grasp. This one's pretty hard, right? You can show that that expression up top, with some clever applied math tricks, is just slightly smaller than this expression. And let me show you how close we really are. If I were to plug in 365 in here, and on the top I showed the exact expression, this one I expect you to be able to do with some pain. This is the one we just got that's a very, very close upper bound. It's very good, right? Why isn't it perfect? Well, because natural logarithm of 1 minus x is not minus x. So this is how much divergence you get. When I said it works as long as it's small, as you go here, you see it's less small. But it is a good bound. And it's a tight, it's an upper bound, and it's a tight bound, very tight. In fact, if I plot it, this is the probability. Note this time it goes down, because this is the no collision probability. All right. This is a very tight upper bound. And so that means if I use this tight upper bound to get the crossover probability, what do you think? Will it be good? Yeah, it's going to be much better than the union bound we got. Okay. All right. So if we wanted to find the probability, or the m that's critical, that where we hit the 50% mark, then it's just, okay, so we can just say, we know this. We know that the probability of A is roughly this number, just ever so slightly smaller. I'm going to do something here where I'm going to be lazy. I've gone from m times m minus 1 to m squared. So I've dropped this little less than sign because I increased this exponent slightly. It's not necessarily still less than, but it's still going to be close. If I plug into this just very similar expression, I still expect it to be pretty accurate. And so to show you some algebra here, I'm going to give you an example how I can compute the critical m. So if this expression works, I showed you a curve that said they track really well. I just do some algebra. So what are the steps? First, I natural logarithm both sides to get the exponent down. Then I move the 2 into this side. And then I take this square root. And I get 1.177 square root n. That's where that magic came from. Okay, again, this is beyond the scope of mere 70 mortals. But it is something that hopefully feels plausible that we're able to arrive at. Okay? And so in the end, we end up with the ability to come up with a close, accurate number. Okay, the very last thing I want to mention before you go, sorry if you're tired, is I have here these 3 different ways of getting the critical m. So the bottom is the actual real critical m using the real curve. The top is using the union bound, which you'll notice is a bit of an underestimate. It's a little too conservative. And here is the upper bound that's very tight. And it works extremely well. So with a lot of clever applied math tricks, we can get a nice expression. Okay. The very last thing I want to mention is you could, if you wanted like 95% chance of no collision, you can get a different expression, like 0.32 times square root n. In general, and this is where we're going to wrap up, if you really wanted to bound how far off you are from having a collision, or the probability of a collision, this is your general expression. So hopefully you found that fun. It's, again, a little beyond the scope of the techniques we'll use in 70, but what I really want you to walk away with is the sense that the union bound is a very powerful idea, and that the product rule is a nice way to get expressions for exact probabilities. There's extra stuff. If you want to do the extra note 17 stuff to decompose the coupon collector and load balancing, I'll be here for questions if you have any. Thank you for going on the algebra journey with me. How you doing? Brain stretch?